Hello, welcome to the imaging component of the neuroscience course. My name is Roy Riascos, and I'm going to talk today about an introduction to neuroimaging. What are the objectives of today? So the first objective is to know the differences between the main images that we look at as neuroradiologists, which are CTs and MRIs. The second one that we should have at the end of the day is to know the correct terms that we use when we speak about the different shades of gray in CTs and in MRIs. And finally, we're going to understand what are the main sequences that we see in MRI so you guys can differentiate it. So this is very important because, as you can understand, it is almost impossible for us to know really what's going on inside of the morphology of the brain unless we had to open it up. Fortunately, we have tools to avoid that, which are diagnostic images. So that's what we're going to be talking about today. So let me kind of take you through a couple of questions before we start to see if you maybe already know the answers. And if not, I think you're really going to enjoy this video. So let's start first with this first image that I'm showing you. So with this first image that I'm showing you, do you know which one is a CT? A, B, C, or D? Maybe it's not that easy. Maybe it is for you. Let's answer another question today, which is from the images that you're seeing here, which are basically the same ones we had in the previous question. Which one is a T1 weighted sequence? A, B, C, or D? Well, if we're lucky, at the end of this talk, you're going to be able to answer these things with your eyes closed. And it's going to give you tools to interpret many, many wonderful things that you can do through magnetic resonance or with CT. So let's get back to the lecture and let's talk about imaging studies. What are the imaging studies that you can do to study the central nervous system, the spine, or in the head and neck, which is what neuroradiology is all about? So we can do it through plain radiographs. You can also do it through fluoroscopy, which is kind of doing cinematic images of X-rays. Another way to do it is through angiography, which is when you shoot dye inside of the vessels, typically the arteries. So you can see vessel maps, and you're actually doing an image, which is a cinematic picture of a radiograph. Another way to do it is through sonography, which we call ultrasound, where you use ultrasound waves to look inside of a patient's body. Because the brain is kind of inside of the skull, it's fairly limited what you can see with ultrasound. However, in babies, since they have the fontanelles open, it's really interesting because you can do direct ultrasound of the baby brains, and we use that a lot. Another way that we can also study is through computed tomography, which is CT, which is really kind of X-rays, and you put the X-rays into a process where you're going to have the detector in the X-rays rotate around the patient, and you can do reconstructions of planes of what's going on inside of the patient. We're going to talk a little bit about that today. And through MRI. So MRI is utilizing magnetism to transfer energy into the human brain, and through that, or the body, but through the energy, the body will just give back that energy. If you tweak it a little bit, we're going to see that in physics in this course. And then you can actually identify intensities of signal inside of the body and reconstruct images. And finally, you could do it by transferring into a pharmaceutical agent, something that emits either gamma rays or protons. You inject it into the patient, and then that's how you do nuclear medicine, which actually the radio emitter is inside of the patient and it emits the radiation. And then you have a special detector that does that. For the most part, for these lectures, we're going to be talking about the two main ones that we utilize, which are going to be CT and MRI. So here's our first question. What is wrong with this picture? So as you can see here in the picture, you have Superman with X-ray vision. That sounds super cool, right? You can see a patient, like if you were looking at x-rays, just with a vision. Well, it's not as easy. Actually, having x-ray vision wouldn't really look like that unless Superman had a super friend on the other side with an imaging detector telling him what was going on. So let's talk about light and let's talk about photons, because that's the principle of understanding x-rays. So we are all used to looking at x-rays or photons in a different way. Typically, you have seen them when they show you guys in the movies, or you see it of people seeing them through an acetate, which is a piece of plastic, and you put it through a view box, and then the view box would show us a grayscale of something inside of a body that had crossed the x-rays through it. Then now we don't do that anymore. You guys see PACs and you see images in computers that actually can show you exactly the same, because we have changed this analog way of doing images through a more modern way of doing images, which is using electronics. So let me kind of go slowly through what's going on and what are the principles of these things. So how are we used to see photons on daily life? Imagine you have a light source, like a light bulb. It will emit photons. Then you have a solid object, and that solid object is going to reflect those photons. And you're going to have a receptor, which is in the back of the eye, which is the retina. And that retina is going to be able to receive the information from those photons, react to them, and create a neural stimulus that is going to go into the cortex of your brain. So that's what photons do. You see them all the time. These photons are very particular. Again, they do not have mass, but they are electromagnetic waves. And these photons can penetrate solid objects. And one of the things that you can see it all the time penetrating is, for example, a window. So if you have a window, even though it's solid, the photons can cross through the window and they're going to impact the retina almost the same way as if the window was not there. And you can imagine that if you have the ground glass part of the window, if a bit of the window is a little bit of ground glass, what you're going to see is that some of the light will cross less freely through the ground glass part of the window, even though you're seeing the photons on the other side, than in the part of the window that is not ground glass. Now imagine that you put a dime in the middle of the ground glass. You see that you're going to have the same representation as what you're seeing in the window in the retina, but the photons will not be able to cross the metal. So what you're going to see is just a dark spot there, because you can really not see the light that is coming from that. So these are photons. Now imagine that we do the same, but instead of doing it with photons that are in the spectrum of light, you do it with photons that are a little bit different. They have slightly increased frequency. And they can penetrate objects more than just the light photons would. That is, in that spectrum is where X-rays live. And what you're doing with X-rays is basically the same thing we were doing with the other photons, where you have an X-ray tube that is emits the photons. And then you have different structures that are going to be in the way of the X-ray tube. And the X-ray tube can either cross it or bounce, depending on the density of what's in there. So if what you have is something very dense, it will bounce. If it's not dense, it will cross easily. The way that our experiment usually started with was that we had a piece of plastic, which was acetate. We put some chemicals into it, which were really silver, and the silver would react to the X-rays. Whereas if the X-rays didn't hit it, it wouldn't react. And wherever it reacted, it would become dark. So what are structures where X-rays cross easily? X-rays cross easily through the air. And structures where X-rays really have a hard time crossing are going to be things that are very molecularly dense. And those are typically metals. So if the metal went into that acetate and it didn't react with the silver, it would just, when you washed it, it would be transparent. So when you put it in a view box, which is white, it would look white. And that's where we get these grayscales that we used to have. Then we just needed kind of to understand what would live in the middle between air and metal, which was really not super dark or very, very, very bright. And that thing was going to be fluid or water. So we put water in the middle, and we would identify structures that were a little bit denser than water, but they were not as dense as metal. One of those structures is typically minerals. The one that we're going to talk about today is calcium, right? And things that were less dense than water, but they were not as hypodense or less dense than air, which was going to be fat. So the result of this is that in the detector, you're going to see things that have a grayscale, scale of things that are from very dark to very bright. And we call those, in X-rays, these are things that are radiodense or radiolucent in case that when they're dark, or radio-opaque when they're very white. And this is the famous grayscale of X-rays. Being white, what we call radio opaque, like metal, and dark, something that we call radiolucent, like air. Easy, the X-rays cross easily through air, very hard to things like metal. So by saying that, Superman here, to have these detectors, would have to have them on the other side. You really could not make that happen. So let's get to the next question, which is there's a diagnostic imaging that is based on X-ray, that is cross-sectional, not just plain radiographs where you just cross the whole body, but you could actually reproduce a cross-section of the body, and that is called CT. So what does CT stand for? Is it categorical? Is it computed tomography? Is it Caterpillar? Or is it convoluted technology? No, it's not Caterpillar. I know you wanted it to be, but no, it actually stands for something else. It stands for computed tomography. Now, computed tomography is based on what technology? I just told you this. And this is going to be very important in your medical practice, because we're going to talk about some of the effects that these photons that are X-rays can have in the human genes and human cells. So because they can harm them if you get exposed to too many of them. So it's really important to know which of the technologies that you're utilizing use X-rays. And this is what we call ionic radiation. So which CT, which is ionic radiation, uses magnetism, ultrasound, radioactivity, which is emitting internally the rays, or is it X-rays? On which of these four technologies is CT based on? Great answer. Yes, it is X-rays. So CT is actually based on X-ray technology. So CT was discovered in the early 70s. It was discovered by a bunch of scientists, but I think the most important one that worked on it was Sir Godfrey Hounsfield, and the other one was Sir Alan McCormack, where it was such an important thing for humanity that they won the Nobel Prize later in 1979. CT is a combination of these images where a computer combines the X-rays as they rotate around a human. You take many X-rays in the same area at very slightly different angles, and as you do that, a computer puts the information together and it can reconstruct a 2D plane where they crossed it. And that, my friends, was very unique. Before that, there was no way you could look inside of a head or inside of a spine before this technology arrived. And it, as you can see, arrived initially in the early 70s, but it was not commercially available until the early 80s. So today, we're in 2024, we have not even had 25 years of having this technology available for our medical practices. The first CT is what you see here. It's called the EMI-1. It was in Atkinson's Morley Hospital in England, and it took 9 days to do the imaging collection. 2.5 hours to reconstruct, and 2 hours to actually display it. So the computer, it was a huge computer room that needed to display that. And this was the first image, the one that you have down here. Let me try to magnify that for you guys so you can see it better. So in this image, you can see that it's kind of oval shaped. That's a head. So the first CT was actually a head. And you can identify inside of the head that we have a space right here, which is which is dark, and that space that I put right there, which is not enhancing, are the ventricles. And then that you also have some space in the sides, which is kind of the brain parenchyma. And there's a little bit a wider rim, and that wider rim is the skull. That was the first time you could see that. And it was absolutely amazing. But look at how long it took. So how does CT technology kind of work? Again, we had this beam, which was an X-ray. You put it into this round structure that went around the patient, and you rotated it with slight different angles, and the detectors on the other side would also do that. And then a computer would just see how the information that was coming from that to reconstruct with very complex mathematical algorithms the images. So we've gone a long way from that. So I brought you a scan from 1972, which we have up here, and kind of a scan of what we are seeing nowadays, which is this was 2017. Our 2D images have not changed much since then, where you can see the huge difference that we have. The scanners have also changed, as you can see there. And nowadays, we have scanners that go all the way to 640 axial images in just one rotation. We can cover almost 16 centimeters of a body part without having to move the table at all. So we can get these type of images in less than a quarter of a second today. So we went from days and hours to have something that is very efficient, very easy to utilize. And of course, the radiation has changed significantly since then. So CTs initially could only do axial planes. That's why it was kind of a limitation of it. So if you put the body inside of the scanner, and the body was going to, and the tube was going to rotate around the body, you could only kind of do axial studies of it. So that in the past was the only way to do it. But nowadays, technology has improved so much that the volume elements that we're receiving from the scanner can have the same depth, width, and height. So if you have a kind of a little cube that has the same depth, width, and height, and you have multiple of those per slice, and you have multiple slides, you can reconstruct the same slice in different planes. So nowadays, we can reformat these in different planes that we couldn't in the past, and that only happened until we were able to do what we call isovolumetric voxels. And what you're seeing and displayed in the computer when you see them is our picture elements or pixels. So these pixels belong to this data set of isovolumetric voxels, and pretty much all of them have that type of technology. So the success of which of the following industries led to the development of CT? Let's see if we know this one. Is it the Scottish oil business? Is it the U.S. space program? Is it the Beatles, the musical group? Or is it Silicon Valley? Good answer. The Beatles. So the Beatles music. So EMI had a grant that was based on, and they were very famous because um, uh, these grants that EMI had because of the great success of their company, and the biggest um, group that was part of their brand was the Beatles. So because of the Beatles, every time that you listen to the Beatles, I hope that you have a little more positive energy towards them. They're very positive in all their music, but thanks to them, CT was able to be born. And this concludes part one of this lecture.